Let us look at the second problem in Nyquist plot. The problem statement goes like this. Draw the Nyquist plot and find the range of k for the system stability where the open loop transfer function is given by g h of s is equal to k divided by s into s plus 2 into s plus 10. So in this particular problem, we need to find the range of k for the system stability. Right. So we know how to plot the polar Nyquist plot. Once you plot the Nyquist plot, then you can find out number of encirclements, and based on the encirclements, then you can find out what will be the k value for system stability. So it is a k adjustment. So what is the Nyquist path for the system? If you look at the system is type 1 system, therefore I can draw the Nyquist path like this. So there are 4 paths here: path 1, path 2, path 3, path 4. What is Nyquist plot? Nyquist plot is mapping of these 4 paths of Nyquist path into GH of S plane. We will start with the step 1, that is the mapping of P1. P1 is path 1. We know that it is the polar plot. What is the transfer function? GH of S is k by s into s plus 2 into s plus 10. Substitute s is equal to j omega. Get what is the sinusoidal transfer function? GH of j omega is k by j omega into 2 plus j omega, 10 plus j omega. Write the magnitude expression. M is k by omega into under root 4 plus omega square under root 100 plus omega square. Then you can write what is the phase angle expression. So for j omega denominator 90, so it is denominator, therefore minus 90 minus tan inverse I have omega by 2 minus tan inverse omega by 10. Now prepare a table. You know the columns are omega, magnitude and phase angle. Substitute omega is 0. Then magnitude is going to be infinity, the phase angle is minus 90. So that is the starting angle, and when you take very small value 0.01, the magnitude is not necessary, then phase angle is minus 90.34, therefore it is above the 90 degrees. That we can observe from here. Then if you take the maximum values, let us say 10,000, it is going to be minus 269.93. So it is in between 180 and 270, the ending angle when it is reaching to. So when it is infinity, it is minus 270. So this is a table available for the given open loop transfer function GH of S k by s into s plus 2 into s plus 10. So from the table available, the data, so we have minus 90 the starting angle and minus 270 is the ending angle. So using this, then we can draw the polar plot. So when you draw the polar plot here, magnitude is infinity at minus 90 degrees. Therefore, minus 90 degrees is this line, and I can take the infinity here. And this is the starting point of polar plot, and ending point is minus 270 degrees. Therefore, so I will have minus 270 degrees, and the magnitude is going to be 0. So I will have polar plot like this. So when it is reaching to the 0, and it is to touch the minus 270 degrees line, and also it is crossing minus 180 degrees line. So this is the polar plot for the open loop transfer function. Next, mapping of path 2. We know that mapping of path 2 is one or more semicircles around the origin with radius r tends to 0. So simply we can ignore it. And mapping of path 3. So mapping of path 3 is the inverse polar plot. So inverse polar plot is the mirror image of polar plot where the direction is continuous. So polar plot is this, the direction is going towards the origin, then we need to take the mirror image with respect to the with respect to the x-axis. So that will be like this. So we have from minus 270 to minus 90 where the direction is away from the origin. So polar plot is like this and inverse polar plot is like this. So we have path 3. Next, path 4. So before going to plot the path 4, look at how many number of poles we have at origin. I have 1 pole at origin, which means we will be having only one semicircle when you map path 4 into the GH of S plane. And also what will be the starting point of the path 4? The starting point of the path 4 is the ending point of inverse polar plot. So inverse polar plot is like this, the ending point is at minus 270 degrees. Now from here to, I need to take up to the starting point of the polar plot in clockwise direction. So what we can say that the path
path 4, when you mapping to the GH of S plane, it will be like this. So this is a point, starting point, and it is taking one semicircle and it is going to your minus 90, which is starting point of the polar plot. So all individual mappings are available. To get the Nyquist plot, we are going to combine all the plots. So when you combine all the plots, it is going to be like this. Now, what is this? Now, what we are interested is, we are interested in the minus 180 degrees line or negative real axis. Your Nyquist plot crossing the negative real axis at this point. And the frequency at this point is called phase crossover frequency, and the distance from the origin to the intersecting point is the MPC. So we need to know what is the MPC value and also what will be the frequency at that point. To find that, let us solve for MPC. We know what is the method to solve MPC. Take the phase angle expression, equate it to minus 180 degrees. So what will the phase angle expression? The transfer function is k by s into s plus 2 into s plus 10. The magnitude is, we have k as it is, and omega under root of 4 plus omega square and under root 100 plus omega square. This is the magnitude, and phase angle is minus 90 minus tan inverse omega by 2 minus tan inverse omega by 10. So this phase angle expression equated to minus 180 degrees. When equated to minus 180 degrees, then when you solve it, you know how to solve this, then we will be getting the omega PC as root 20. And that means the frequency at which the Nyquist plot crossing the minus real axis or negative real axis or minus 180 degrees line is the phase crossover frequency, which is root 20 radian per second. Now substitute this omega and in the magnitude expression. When substitute in the magnitude expression, you will be getting the MPC. The MPC is nothing but k divided by 240. So this MPC is the magnitude, which means the distance from the origin to the intersecting point. But what will be the point? When I take real and imaginary axis, what will be the point? The point is nothing but minus k by 240 plus j0, because on the real axis the imaginary part is 0. So the point intersecting is minus k by 240 plus j0. I need to find what will be this k value to have the system stable. Let us take 3 different cases. The first case is, let us assume k is equal to 240. When k is 240, what is the intersecting point? Intersecting point is going to be minus 1 plus j0. So your Nyquist plot is passing through the critical point. So whenever the Nyquist plot passing through the critical point, then closed loop system is said to be marginally stable or critically stable. The system will have continuous oscillations, and at that particular k value, in this case k is 240, we will be having one or more non-repeated poles on the imaginary axis. This is a critically stable or marginally stable condition. K is 240. Now second case is, let us take k is greater than 240. When you take k is greater than 240, what will be the intersecting point? So the intersecting point is not important, but where will be the critical point? The critical point will be inside this or outside this. So when k is greater than 240, it is clearly, we know that the critical point will be inside this. So now from the critical point, I am going to draw a line towards the left direction and see how many intersections it is making. So when you look at this, we have 2 intersections which it is making. What are the 2 intersections? One is which is having this inner circle, one is which is having the outer circle. So what will be the inner circle direction? It is towards the origin. So this is nothing but your anti-clockwise, and when it goes outside, then we will have like this, means it is a clockwise direction. So one is a clockwise, other one is anti-clockwise, which means my n is nothing but 0. So in this particular case, the n value we are getting 0 when k is greater than 240. Then when you take k is less than 240. When you take less than 240, the critical point will be the outside. So when critical point is outside, then how many intersections we have? We don't have any intersections, therefore n is equal to 0. Let us take the second case where k is greater than 240. So when k is greater than 240, what is the intersecting point? So if we take any particular k value, we will know what is the intersecting point. But what I am interested is not the point, where will be the critical point. The critical point is inside this circle or outside this. So when k is greater than 240, it is clearly, we can say that the critical point will be inside the circle. Now from the critical point, you draw the line towards the left direction, see how many encirclements we have and what will be the encirclement. Now when you draw the line here, when you look at the inner circle direction, and it is going to be clockwise direction at that particular point. Similarly, when you take the outer one, and again we have a clockwise direction, means both are clockwise, I can say n is equal to -2. So if encirclements are anti-clockwise, n is positive. If encirclements are clockwise, n is negative. Therefore, in this case, two encirclements in clockwise, n is equal to -2. So what is your formula? Z is equal to P minus n. We know that P is 0 in this case. The transfer function is k by s into s plus 2 into s plus 5. No open loop poles are lying in right of the s plane. P is 0. And n is equal to -2, the z is equal to p minus n. So 0 minus of -2, z is going to be 2. So z indicates how many number of closed loop poles that are lying in the right half of the s plane. So there are 2 poles in the closed loop poles lying in the right of the s plane, which means my closed loop system is unstable. So when k is greater than 240, the closed loop system is going to be unstable. Case 3. In case 3, let us take k is less than 240. When you take k less than 240, my critical point is away from the circle. So when it is away from the circle, when you draw one line and there are no intersection at all, n is equal to 0. So we know p is 0, and from this n is 0, z is also 0. Therefore, there are no closed loop poles which are lying in right half of the s plane. So closed loop system is stable. So from this analysis, then we can say that the closed loop system is going to be stable if the k range in between 0 and 240. When k is 240, system is marginally stable, and k is from 240 to infinity, the closed loop system is unstable.